Let us continue with the concept of a moment of force. So the concept really is just that moment is equal to a force times a distance. So the simplest case is where they give you a force and they give you the distance. You have to check that the distance is perpendicular to the force. So in a case where you have a fixed, say a fixed beam, and you apply a force, okay, the moment is from the point of the force to where the or where you want to measure the moment at. So moment at O is distance L times a force F. Notice that this is rotating clockwise, therefore this is going to be a negative moment. If, on the other hand, you have the same beam, but the force is applied in a way that you're going to try to rotate it counterclockwise, then the moment at O is positive. And that is because it's rotating counterclockwise. All right. There's another aspect that you have to know, which is if a force is applied through the axis, okay, then in this case, there's no perpendicular force, so moment at O is equal to 0. And a lot of problems will have this scenario, this case. When you have a example, you have a beam and a force is applied at a certain angle. So when you find the components of F3, you're gonna have F3x and F3y. Okay, but notice that F3x is parallel to the axis. F3y is perpendicular to the axis. So the moment because of F3x is equal to 0. And the moment because of F3y is the same, it's just the case of F3y times L. Okay? Moment of F3y is equal to F3y times L, and is negative. Okay, so this is all we're saying here is O could be the point where you want to measure the moment at, could be anywhere. Doesn't have to be the origin, doesn't have to be the fixed point. As long as you know the distance and the force that is perpendicular to it, you're good. Also, the force does not have to be exactly at the point where you're measuring the distance. As long as the force crossing through that point, you can measure it. Remember that you can move forces around in statics because they're basically keeping the system in equilibrium. And we just talked about the sign. If it's clockwise is negative, if it's counterclockwise is positive. Okay, so that's Ragnon's theorem. Basically, if you have a vector r that is giving you the distance of the force, so vector r is in meters or inches or feet, but its distance is units of length. And you have, this is a vector, then you have the cross product. A bunch of forces, F1 plus F2, etc. The theorem says that it's the same thing to have the vector r times each force, than if you add all the forces together and do the cross product. So in that case, you can add all the forces together by components. So you can have the components in x and y and z, and add all the x, y, and z components, and at the end you can find the moment at O. So the vector r will give you, remember, head minus tail. It will give you the distance of the force. So this is a good example. We have point A, where we know the distance r, or we can measure the distance r, or at least we can compute it, and then we find the components fx, fy, and fz. Then the moment is the cross product of r and f, and we know that that looks like this: I, j, k, the distance x, y, and z, and the force fx, fy, fz. We know how to get the forces by the cosine and sine of the angles. Okay, then the moment, remember all these x, y, and z coordinates are in meters or units of length, and all these forces are newtons or pound force. Therefore, moment is going to be Newton meters. Hence, the solution is I multiplies f z times y minus f y times z minus j multiplies f z times x minus fx times z plus k that multiplies fy times x minus fx times y. So remember, it's very simple. The first time is I, so you cancel this column, cancel this row, and it's y times x minus z times fy. It's just like a game. Minus j, cancel this row and this column, and you have x times fz minus z times fx plus k, cancel this row and this column, and then from these four elements you have x times fy minus y times fz. Just by convention, I put the force first and the distance second. Okay, so that is basically what we get here. Let's double check that this is what we get. Let's see. Double check. Okay, so let's move this around. All right, so is fz times y correct? Minus z times fy, yes. Minus, okay, so be careful here because you can do it wrong. You can do this iteration incorrectly. Is minus fzx, and they're saying plus, but the minus is here, fzx. And then plus, because minus times minus is plus, fz times z, or fx times z is right here. And then plus fy times x, correct, minus fy times fx times y. Okay. And then of course that will give you the moments in x, y, and z by taking each component. So evidently this part is the moment around x, this one is the one around y, this one is the one around z. and the math will tell you if it's positive and negative. Sometimes it's not that easy to see the way it rotates. Okay, so that is basically okay. This one is a very good example because B is not at the origin, so we have to find the coordinates of A and B. So R A B. I don't know why they do that slash. I don't. It's a confusing. It's like you're dividing A over B, and it's just confusing. So this is R A to B has obviously distances in X that go to I, Y, and J, and Z, and K. So if you remember, it's head minus tail. So for X, you have XA minus XB. For Y is YA minus YB. And for Z, you have ZA minus ZB. That will give you the distance in X, Y, and Z. And when you do your cross product, it's simply XA minus XB, YA minus YB, ZA minus ZB. Of course, these are numbers, I, J, and K, and Fx, Fy, Fz. So for instance, if this vector is going from 0x, 0y, negative 5z to the head is 10x, 5y, 3z, then you just put xa is the head, the x at the head, and xb is the x coordinate at the tail. And then you just do this operation as we just did. Okay, just like that is showing. Perfect. So here we're seeing that this distance r with this component fx is giving you a perpendicular moment. Okay, so a distance r cross the product, the component fx will give you a perpendicular moment. We saw that already. So this is a good example that you can go over it in your book, example 3.1. They're asking you what is the, well, different things. They're telling you 100-pound force is applied to the end of this tool. So determine the moment about O. So if you notice, there's different things that they can ask here. A is the moment about O. The second one is the horizontal force at A. This third question is the smallest force at A to produce the same moment. D is the location of 240 pound to create the same moment. And C, whether any point from B and C and D are equivalent to the original force. So any of these solutions equivalent to the original force. So the moment about O, the moment about O is pretty straightforward. First, the sign, if you try to rotate this, it's going to be clockwise. Therefore, we should have a negative moment. And the perpendicular distance to this force is D. So we need to find D, which is the cosine of the angle times the hypotenuse. So 24 inches times cosine of 60. Now, a lot of times, you notice that this is just very easy. A lot of times they'll give you the distance in meters and the force in pounds. Or they give you the force in newtons and the distance in inches. So you have to convert the units. Say it was 24 inches, you have to transform to meters. You know that 25.4 millimeters is 1 inch, and etc. But in this case, we have inches and pound force. We're good. So the distance is, this distance is 12 inches. Therefore, the force perpendicular to it is 100 pounds. So the moment is negative 12 inches times 100-pound force, which is 1200 pound inches. Okay. Question B, the horizontal force. All right, well, in that case, we have to find what is the component of the force in X. So originally, we had a force that it was 100 pounds, and we have an angle of 60, and we have, this is the force that they're asking for, Fx. So the first thing we have to do is notice that we have different things to do here. If we want to find this force, we can do it by the cosine of the angle, but we have to know what is the force here. Another way to do is just with the distance. So this distance from here to here, we can find it by the sine of the angle. So 24 times sine of the angle, which is 60, is equal to 20.8. Okay, 20.8 inches. Now that we have that distance, we simply apply the force and the distance gives us that moment. However, notice that we know the moment already. We're saying that from that moment, they're saying that same moment produces the force at A. So what is that force? Okay, so moment equals force times distance. And we know that that one is 1200 pounds inch is equal to Fx times the distance, that is 20.8. So Fx is equal to 1200 divided by 20.8. This is inches, this is pound, inch, so inch and inch go away. Fx is equal to whatever that division is, 58 pounds. So notice that that force creates the same moment with 58 pounds, which is not very much, versus this force creates the same moment with 100 pounds. So if you were trying to create this, if you're trying to use this tool, this force right here will not, you'll have to be pushing harder than if you go this way. If you just try to push from this force right here. Okay, so the moment is the same, but the forces are different. And in case C, what is the smallest force at A? So basically what they're saying is if the moment is 1200 pound inch, then we have to decide two things. What distance we want to use. And the distance is basically, the distance has to be perpendicular to it. So we know that if the longer, so this is really the trick. Here is linear. We have a force and a distance. To get to the same number, if they're asking for the minimum force, then distance has to be maximized. And this distance was only 12, and this distance was only, I already forgot, let's see. This was 20, but notice that this distance is 24. So the force perpendicular to that distance is right here. So using the distance of 24, we have 1200 divided by 24, which is 50 pounds. So the minimum amount of force that you need to do is 50 pounds, which is half of this force, the original one, which was 100 pounds, just by changing the direction of the force. So that's pretty interesting. D, determine the point of application of a 240-pound force to produce the same moment. Okay, so say there was a wall right here or something that you couldn't push. You couldn't put your hand on this end, and you need to apply the same amount of moment. They're asking you if the force is 240 pounds, what would be the same moment, which is pretty easy. You have the moment is the same as 1200 pound force times inch equals 1240 divided by distance is just dividing 1200 divided by 240, which is equal to 5 inches. This guy is equal to 5 inches, which is interesting because by doubling the distance, it was 100 pounds. It's not 120, so it's not quite double because the distance is with respect to the cosine of the angle. It would be half if it was perpendicular to that force because the distance is linear, but here the distance is a component of the main axis. Okay, make sure you understand this part. And then what is the distance OB? It's pretty simple. You already have 5, so OB is equal to 5 cosine of, sorry, the other way around. I apologize. So D is equal to OB times cosine of 60. Then we simply have to solve for OB. So 5 divided by cosine of 60 degrees is equal to OB, which is saying that is this distance is 10 inches. E. So although each of the forces in part B, C, and D produce the same moment, none of the same magnitudes, none of them are the same magnitude and sense or direction, basically. One of the forces is equivalent to the 100-pound force. So, well, yeah, they're really not they're not asking really a question here. They're just going over the whole problem, saying if you change the direction, if you change the force, if you change the angle, any of those things will change the moment. The same thing, if you change the moment and start moving the distance around, your force will have to change. Okay. Now this one is pretty interesting because we have a 3D force, and now we have to find the components. So let's say we have a force right here, tension, and the origin is right here. So let's find, so basically what we have to do is say this is tension from head is D and C. Let's make sure that they're doing the same thing. C and D, yeah. Okay, that's the tension right there. Okay, so the rectangular plate is supported by the bracket at A and B. From, yeah, so the supports for the plate are A and B, but there's only a wire CD that is supporting a tension of 200 newtons. To tension at DC equals 200 newtons. Determine the moment about A. Oh, interesting. So we have to find this moment about A. So basically they're asking for R, A, C. Yep. So, and just to keep the same answer, but the same sign is going to be CA. They wanted to do CA, it's fine. It will be the same distance, just different, the opposite magnitude. So the moment is RCA times the force, which is the tension from D to C. So the first thing we have to do is find RCA. So the point C has coordinates in X and Y and Z. Okay, so X is 0.3 meters, and Y is 0, and Z is 0.08 times 0.24 is 0.32, so 0.4. Okay. Point A has X is 0, Y is 0, and Z is 0.32 meters. All these things are in meters. So RCA is equal to the head minus the tail. 0.3 minus 0 is 0.3 in I, comma, 0 minus 0 is 0 in J, comma, and 0.4 minus 0.32 is 0.08 in J. Go ahead and use your calculator if you're not sure. And if we compare, we have 0.3 in X, no J, and 0.08 in K. Okay, so we have the first part right. We need the second thing, force. So for this force, we're gonna do the tension of C to D times lambda C to D. And remember that lambda is the direction divided by the unit vector. So lambda CD is equal to RCD vector divided by the magnitude of RCD. All right, which they computed already, and they have, well, so let's go ahead and compute it ourselves. So the point C we already have, so let's do this C. Actually, let's do D. X, Y, and Z. So D is 0 in X and 0.24 in J and 0.08 in K. All right. Let's double check. D is 0x, and Y we do have, yep. And point C is 0.3, comma, 0, comma, 0.32. JK. All right, so RCA is equal to 0 minus 0.3 is minus 0.3 in I, comma, 0.24 minus 0 is 0.24 in J, comma, 0.08 minus 0.32 is minus 0.24. All of this is in meters. And this is K, the direction K. All right, so what we have to do now is find our CA magnitude, which is the square root of negative 0.3 squared plus 0.24 squared plus negative 0.24 squared. I'm using my calculator, but you can use Wolfram Alpha. Okay, so we have 0.3, 0.24, negative 0.24, and we get 0.45. Is that true? Yeah, they get 0.45. Okay. So that's what we get. They get 0.5, but that's just trust their computations. 0.45 meters. All right. So lambda. Let's continue. Let's continue on this other side. Lambda is equal to 0.3 or negative 0.3 divided by this number, which is 0.66 minus 0.66 in I, 0.24 divided by 0.45 is 0.52 positive, and 0. This is the same but negative, negative 0.52. So what I did is this computation is 0, negative 0.3 I, comma 0.24 j, comma negative 0.24 k divided by 0.45. All this is in meters and all this is in meters. Therefore, meters cancel out, and we have a unit vector with I, j, and k components, which is this guy. So our force is equal to 200, 200 newtons times lambda, which is equal to, let's see, times 200, 132.4, 132.4 negative 132.4 newtons, comma, times 200, it's 105 times 106, j, comma, negative 106. Okay. Okay, so that's our force, or tension at CD. Lastly, what we have to do is the moment, which is moment equals I, j, k of the vector RCA, which is 0.3. No, I'm sorry. The vector is not the vector CA, is the vector C. Yeah, it's the vector CA. 0 and 0.08, which is this vector right here from A to C. Alright, and the force is the tension at CD. And that tension was negative 132.4 106, negative 106. So all these things are in meters, 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 and these ones are in newtons. Because what we're doing is RCD plus tension at, CA in tension at DC. RCA tension, let's do it again. This is equal to RCA head minus tail vector cross tension vector head minus tail DC. That is what we did. So the moment is going to have a component in I with 0 minus cancel 0 times negative 106 is 0 minus 106 times 0 0.08 and that is 8.48 Newton meter in I minus cancel J is 0.3. Well, let's do that. 0.3 times negative 106 is negative 31.8, negative 32 Newton meters plus, sorry, nope, it was minus 0.08 times minus 132. It's negative 10.5. And J plus, cancel K, 0.3 times 106. 31.8, 32 minus 0 and K with units of Newton meter. Okay, so let's go ahead and try to do this again. So this one is in I is 0 minus 8.48 Newton meters minus 32 plus 10.5 is negative 21.5 plus 32 and K, J and I. Okay. All right. So this it means that the moment has components of negative 8.48 I, comma 21.5 J, comma 32 K newtons per meter. And if we did everything correctly, we should have negative 7.6, well, that's close enough, plus 28, we got 21, plus 28. Okay, so what did we do wrong? It's not as close as I would like. So they got the force here is negative 120. Why is their force so far apart? So 0.3 0.3, yeah, that's what we need. Oh, wait a second. I know why. It's because we have, oh, yep, I know what the mistake is 0 and 0. And we did not say 0 here, so this is 0. Whoops, so if I do 0, so square root of 0 0.3 squared plus 0 0.25 squared square root of, this one is RCA, is 0. RCA is 0 0.3 and 0 0.8. No, that's true, we get that. This is RCA, and then the distance of the tension is CD, and CD for them gives them 0 0.3, 24. Oh, I see. Wait, what did we do wrong here? Why are we saying that it's 24 and 24? They say is 0 0.3, 0 0.24, and negative 0 0.32. And they're saying that that is RCD. See, this is always the problem. Getting this vector right here is not as easy as it seems. So they're saying that RCD is equal to point D as coordinates 0, 0.24, and 0.08, and C has coordinates of 0.3, 0, 0.08 plus 0.4. Oops, I think I see 0.08 plus 0.24 plus 0.08 is 0.4. So RDC is equal to 0 minus 0.3, 0.24, 0.08 minus 0.4 is negative 0.32. Yeah, this is correct. Okay, well, that means that I have a huge typo here. This is not 24. This is negative 32. Negative 0.32. Alright, so when we do our unit vector, it's going to be 0.24 and negative 0.32. Whoops. Negative 0.32. Okay, so let's do this again. Square root of squared plus, so what are the values? It is negative 0.3 squared plus 0.24 and 0.32, negative 0.32. Okay, that gives us exactly 0.5. Yep. Alright, well, so this is 0.5. That means that over here, this one is 0.5, and all these things need to be fixed. 0.5. 0.3 divided by 0.5. 0.6. Negative 0.6 I. This is meters. No, this is unit vector, unitless. 0.24 divided by 0.5. 0.48. 0.48. And CD is negative 0.32. 0.32 divided by 0.5 is negative 0.64. Alright, so 200 times 0.6 is negative 120. negative 120. 106 is not going to be correct, and this is not going to be correct. Let's go back and say 0.48 times 200 is 96, and negative 0.64 times 200 is 128, negative 128. 120, 96 negative, yep, okay. So this part needs to be fixed as well. All right, so so you can see how really most of the issues are just by getting the right components. Okay, actually I have to raise these two. All right, let's try it again. So this one is negative 120, 96, negative 128. All right, so that will mean that we have here, so 0, 0 minus 0.08 times 96, 7.68 minus 7.68 in I minus, cancel that and cancel that, 0.3 times negative 128, negative 38.4 minus 0.08 times negative 120, 9.6. Okay, so it's 0.3 times negative 128, and yeah, that's correct. And this is Nj plus, for K, we have 0.3 times 96, which is 28.8, minus 0. Okay, so this is negative 7.68 in I, and this is negative 38.4 minus negative 9.6 is negative 28.8 times minus is plus 28.8 in J plus 28.8. Okay, is that true? Let's check. Yes, negative 768, 28.8, 28.8 Newton meter. Okay, well, so conclusion, just make sure you get the coordinates correctly. We weren't way off just because these numbers are small, but these, if this distance is kilometers, then of course we'll be completely wrong. So be careful and please go over this example so you try to memorize the mechanisms that you need to know for solving these type of problems.